The theory of cosmic inflation states that in the first moments after the Big Bang, roughly between 10 to the negative 32nd and 10 to the negative 29th seconds after the event, the universe underwent an exponential expansion. This rapid inflationary phase would have expanded the universe by at least 10 to 27, smoothing out all the initial irregularities and leading to a nearly homogeneous and isotropic universe. This theory solves several puzzles in cosmology, including the flatness problem, the horizon problem, and the absence of magnetic monopoles. One of the key pieces of evidence supporting the inflation theory is observations of the cosmic microwave background radiation. Detailed measurements by instruments such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite have revealed temperature fluctuations in the microwave background that correspond to quantum fluctuations in the density of matter during inflation. These fluctuations eventually developed into the large-scale structure of the universe, such as the galaxies and galaxy clusters we observe today. In addition, inflation theory provides an explanation for the observed homogeneity of the cosmic microwave background over vast distances. Without inflation, regions of the universe now separated by billions of light-years would not be able to exchange information or energy because of the finite speed of light, resulting in significant temperature differences. The inflationary model, however, assumes that these regions were once in thermal equilibrium and then rapidly expanded and became disconnected. Finally, the presence of gravitational waves, which are predicted to occur during inflation, offers another aspect of potential evidence. Early tidal waves, if detected, would be a clear sign of an upwelling period and would further support this theory. New experiments, such as BICEP and upcoming LIGO observations, aim to study this inflation phenomenon. Overall, the theory of global expansion nicely integrates multiple viewpoints and provides a powerful framework for understanding first-world dynamics. The emergence of the universe was important in shaping the early universe and the basis for its creation. In the first moments after the Big Bang, rapid inflation caused all the changes in the distribution of matter and energy. This process allowed for a nearly homogeneous universe, which fostered the conditions necessary for the consistent structure we see today. By increasing homogeneity, inflation laid the foundation for the subsequent fluctuations that were necessary for the formation of galaxies and other cosmic structures. As the universe inflated, tiny quantum fluctuations in the energy field produced regions of slightly varying density. The density fluctuations that occurred after inflation were the seeds from which all subsequent large-scale structures developed. After inflation ended, the universe shifted to a smoother expansion, allowing these fluctuations to grow under the influence of gravity. Over billions of years, the gravitational pull of these denser regions attracted more and more matter, leading to the formation of stars, galaxies, and galaxy clusters. Inflation also contributed significantly to the homogeneity of the universe on large scales. By stretching all existing density variations beyond perceptible levels, inflation erased potential disturbances that could have hindered or prevented the growth of structures. This allowed regions of the cosmos that are now separated by vast distances to once be in close contact, allowing them to have similar properties despite their current uniform distribution. In addition, inflationary theory also helps explain the flat shape of the universe. The rapid expansion would flatten out any curvature, resulting in the near-perfect spatial geometry observed today. This characteristic supports the idea that the universe is in a critical balance between open and closed fate, reinforcing the prevailing idea that we live in a flat universe that continues to evolve under the influence of dark energy. Inflation is thus a cornerstone in our understanding of the early universe and how its complex structure was formed. The end of the inflationary epoch is thought to have been caused by the rapid decay of the inflationary field. whereby the energy driving inflation turned into ordinary matter and radiation. This process is often referred to as reheating. During inflation, the scalar field, often called the inflaton field, dominated the universe and provided the energy needed for exponential expansion. When the dynamics of this field changed, it led to a rapid decrease in its energy density. As the inflaton field decayed, its energy was transferred into particles, creating a hot, dense state filled with a mixture of elementary particles. This event marked the transition from inflation to the so-called hot phase of the Big Bang. After reheating, the universe was filled with high-energy plasma composed of quarks, electrons, neutrinos, and other fundamental particles interacting at incredibly high temperatures. After the inflaton field ended and the universe entered the hot phase of the Big Bang, it continued to expand and cool. As the temperature decreased, quarks began to form protons and neutrons, and these baryonic particles eventually combined to form light nuclei during a period known as Big Bang nucleosynthesis, which occurred within the first few minutes. At this time, elements such as hydrogen, helium, and small traces of lithium were synthesized, laying the foundation for the chemical elements that eventually formed stars and galaxies. As the universe continued to expand and cool, about 380,000 years after the Big Bang, it entered an epoch known as recombination. During the recombination process, electrons combined with protons to form neutral hydrogen atoms. This event allowed photons to move freely through space, giving rise to the cosmic microwave background radiation we see today. This rich tapestry of events initiated the evolution of the universe to its current state, leading to the formation of large-scale structures through gravitational attraction over billions of years. The possibility of multiple periods of inflation in the early universe is a topic of great interest and debate among cosmologists. Although the standard theory of inflation assumes a single, rapid inflationary event, some models suggest that there may have been several inflationary episodes, each with different features and consequences for the structure of the universe. One motivation for considering multiple periods of inflation is some theoretical concepts, such as chaotic inflation and perpetual inflation. Chaotic inflation suggests that inflation can occur repeatedly in different regions of space due to variations in the inflaton field. According to this scenario, while some regions of the universe undergo a short-lived inflationary phase, others may remain in a state of inflation for long periods of time, leading to the concept of a multiverse in which there are multiple bubble universes, each with its own physical properties. Eternal inflation implies that the inflaton field is not set to a stable state everywhere at the same time. In contrast, some regions of space may stop inflating, while others continue to inflate indefinitely. This asymmetric behavior implies that the universe can be characterized by an infinite number of inflationary bubbles, giving rise to a multiverse where each bubble can have different properties, laws of physics, and space-time structures. The consequences of repeated inflation are profound. If true, they could explain the observed homogeneity of the cosmic microwave background and simultaneously explain the anisotropies observed in it. Multiple inflationary events can also help to clarify some of the observed large-scale structures and the distribution of galaxies across the cosmos. Although the concept of multiple inflationary periods remains speculative, researchers are actively exploring both observational and theoretical possibilities to test these ideas. Current and future observational data, such as measurements of the cosmic microwave background and potential primordial gravitational waves, may provide insights that will help distinguish between single and multiple inflation scenarios, ultimately deepening our understanding of the early evolution of the universe. Cosmic inflation has profound implications for the ultimate fate of the universe, affecting how we understand its long-term evolution and structure. The rapid expansion of space during the inflationary epoch not only provided the basis for the observed homogeneity of the cosmic microwave background, but also affected the dynamics of matter, dark energy, and the overall cosmic expansion. One of the key implications of inflation is its connection to the concept of dark energy, which is thought to be the driving force behind the accelerated expansion of the universe. The inflationary model assumes that after an initial inflationary phase, the universe moved into a more stable, gradually expanding state. If dark energy continues to dominate the energy density of the universe, it will likely continue to expand indefinitely. This outcome is often referred to as the Big Freeze or heat death, where galaxies drift farther apart and the universe cools over trillions of years. Eventually, stars will exhaust their nuclear fuel and galaxies will fade away, leading to a cold and rarefied universe. On the other hand, if inflation leads to a multiverse, each bubble universe may follow its own development path. From this perspective, different regions may experience different rates of expansion or changes in physical laws, making the ultimate fate of our universe one of many possible outcomes. This is consistent with some interpretations of quantum mechanics and cosmology, where infinitely different results can arise depending on the initial inflationary conditions. In addition, some inflationary models suggest a cyclic behavior in which the universe may go through several phases of expansion and contraction. In this scenario, the universe could collapse periodically, leading to a large collapse followed by another inflationary phase. Although this concept challenges our current understanding of cosmic expansion, it suggests that the fate of the universe may be more dynamic than a simple linear progression toward a cold, empty outcome. Ultimately, the effects of cosmic inflation on the fate of the universe continue to be an active area of research. As observational techniques and theoretical models evolve, we will be able to understand whether our universe is on a path toward eternal expansion, a cyclic future, or an entirely different scenario that awaits discovery. Each of these possibilities emphasizes the complex relationship between the initial conditions set by inflation and subsequent cosmic evolution. At a fundamental level, gravity is understood within the framework of the general theory of relativity proposed by Albert Einstein in the early 20th century. According to this theory, gravity is not simply a force acting at a distance as previously thought, but rather a curvature of space-time caused by the presence of mass. Massive objects, such as planets, stars, and galaxies, warp the surrounding fabric of space-time, creating a well that affects the motion of other objects in that warped space-time. This means that when an object, such as a planet, moves through space, it is not directly attracted to another object by force in the classical sense. Instead, it follows a path determined by the geometry of the space-time around it. This concept is often illustrated by imagining a heavy ball placed on a stretched rubber sheet. The ball creates a depression that affects smaller objects nearby, causing them to roll toward the larger mass. This curved geometry explains how planets revolve around stars, how galaxies interact, and even how light bends around massive objects, a phenomenon known as gravitational lensing. While the general theory of relativity provides a deep understanding of how gravity functions at large scales, there remains a desire to understand gravity at the quantum level, especially in the context of quantum mechanics. At these scales, particle behavior is governed by quantum fields and probabilities. Physicists have hypothesized that a particle called a graviton would mediate gravitational interactions in a quantum system, much like photons mediate electromagnetic interactions. However, the graviton remains a hypothetical phenomenon because a unifying theory that seamlessly combines gravity with quantum mechanics has yet to be developed. Modern research in theoretical physics seeks to reconcile these two frameworks. Approaches such as string theory and loop quantum gravity offer different models to describe the fundamental nature of gravity. Understanding gravity at the most fundamental level not only expands our understanding of how the universe works, but also affects our understanding of black holes, the behavior of galaxies, and the nature of space-time itself. While scientists seek answers to these profound questions, the quest to understand gravity may eventually reveal deeper layers of reality in the cosmos. The connection between gravity and the curvature of space is at the heart of Einstein's general theory of relativity. Under this concept, according to Isaac Newton, gravity is not seen simply as a force of attraction acting between masses. Instead, they say that the force is the warping force of space created by objects with mass. This revision of gravity will change our understanding of how massive objects interact with each other and affect the orbits of other objects, including the Moon. When mass exists, it changes the geometry of space around it because of the influence of mass. This curvature can be thought of as a fabric that bends in the presence of heavy objects. For example, if a star or planet is in this fabric, it causes a dent or depression that affects nearby objects. When a smaller mass, such as a satellite or another planet, approaches this curved region, it will move along trajectories dictated by the curvature, like a marble rolling in a shallow bowl. This motion manifests itself as orbital motion, such as that of planets around a star. The degree to which space-time is warped depends on the mass of the object and the density of the surrounding space. Denser masses create a stronger curvature, resulting in stronger gravitational effects. Light that travels along the straightest paths in space-time, called geodesics, is also affected by this curvature. When light passes near a massive object, such as a galaxy, it is bent due to the distortion of space-time caused by the mass of the object, a phenomenon seen in gravitational lensing. By describing gravity in terms of space-time curvature, the general theory of relativity provides a comprehensive understanding of various gravitational phenomena, including the precession of planetary orbits, the behavior of objects in strong gravitational fields, and the effects observed near black holes. This relationship emphasizes the interrelationship of mass, space, and time, showing that gravity is an intrinsic feature of the basic structure of the universe. The equations governing these principles, known as Einstein's field equations, are still the cornerstone for understanding cosmological phenomena and the fundamental nature of reality. The concept of extra dimensions of space, beyond the usual three spatial dimensions, is a fascinating aspect of modern theoretical physics. Some modern theories, such as string theory and various higher-dimensional space-time models, suggest that additional dimensions may exist but remain hidden from our direct observation. These theories posit that the fundamental constituents of the universe, subatomic particles, are actually tiny, vibrating strings or membranes that require more than 3 dimensions to fully describe their behavior. String theory, for example, typically requires 10 or 11 dimensions for mathematical consistency, with additional dimensions that can be compacted or convolved so tightly that they are imperceptible on everyday scales. Within this framework, extra dimensions can affect the properties of particles, such as their mass and charge, by changing the way strings oscillate in these dimensions. The implications of such extra dimensions may answer open questions in physics and unify fundamental forces, including gravity, electromagnetism, strong and weak nuclear forces. The idea of extra dimensions can also help explain phenomena such as the relative weakness of gravity compared to other fundamental forces. If gravity propagates through these extra dimensions while other forces remain confined to familiar three-dimensional space, this could explain the apparent weakness of gravity at macroscopic scales. This view is known as the brane world scenario, implying that our observable universe may be a three-dimensional brane embedded in a higher dimensional space. While these theories are compelling and mathematically intriguing, direct experimental evidence for the existence of extra dimensions remains elusive. Researchers are conducting high-energy physics experiments, such as those at the Large Hadron Collider, to look for signs of extra measurements. For example, deviations from expected particle behavior or the formation of mini black holes. In addition, cosmological observations and studies of gravitational waves may provide clues about the properties of the universe that may indicate the existence of extra dimensions. Exploring additional dimensions raises profound philosophical questions about the nature of reality and our perception of the universe. If the existence of these dimensions turns out to be true, it will significantly alter our understanding of the fundamental physics and architecture of the cosmos, leading to a deeper insight into the very fabric of reality. Quantum gravity is designed to bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that describe the universe on very different scales. General relativity effectively describes the gravitational interaction of massive objects in smooth, continuous space-time, and quantum mechanics governs the behavior of particles at the atomic and subatomic levels, where interaction is governed by the laws of probability. Despite successes in their respective fields, these theories have shown incompatibilities in phenomena such as black holes and the very early universe, where both gravitational and quantum effects are important. One of the main approaches to quantum gravity involves the idea of unifying these two frameworks through a theory that views space-time itself as a dynamic, quantized entity. In this context, space-time may not be a smooth canvas as depicted in the general theory of relativity, but rather a frothy structure composed of discrete Planck-scale units. Researchers have proposed various models, such as loop quantum gravity and string theory, to reflect this idea. Loop quantum gravity, for example, assumes that space-time is quantized into tiny loops or networks, which allows gravitational fields to have discrete values and provides a framework for describing gravity without relying solely on the classical geometric interpretation of space-time. String theory also seeks to reconcile these two realms, arguing that the fundamental building blocks of the universe are one-dimensional strings rather than zero-dimensional particles. These strings vibrate at different frequencies, and their specific vibrations correspond to different particles. String theory inherently involves gravity due to the presence of gravitons. Hypothetical quantum particles mediating the gravitational interaction offer a way to incorporate gravitational effects into the quantum structure. A successful theory of quantum gravity could resolve several key problems arising from the merger of general relativity and quantum mechanics. For example, it can provide insight into the nature of singularities found in black holes, where the laws of physics seem to break down. It can also clarify how information is stored in black hole scenarios, potentially offering a solution to the black hole information paradox. Ultimately, the development of a consistent quantum theory of gravity has the potential to enrich our understanding of the fundamental mechanisms of the universe and reveal a unified description of all fundamental forces: gravity, electromagnetism, and nuclear interactions, allowing physicists to explore deeper questions about the nature of reality, space, and time. While researchers continue to explore these concepts, the search for quantum gravity remains one of the most profound and exciting challenges in modern physics. The holographic principle is a fascinating insight into the nature of space-time, suggesting that our three-dimensional universe may be a projection of information encoded on a two-dimensional surface. This idea challenges traditional notions of space and time by arguing that the information contained in a volume of space is not simply stored within that volume, but correlates with data at its boundary. Such a perspective changes the way we think about gravity, black holes, and ultimately the fabric of the cosmos. One of the most striking implications of the holographic principle is its connection to black holes. According to this principle, information about what falls into a black hole is not lost. It suggests that information is instead encoded on the event horizon, the boundary around a black hole. This idea is consistent with the results of quantum mechanics, which suggests that information cannot simply disappear, with profound implications for theories about the fate of matter and energy in our universe. Moreover, this principle implies that space and time, as we understand them in our everyday experience, may be emergent phenomena rather than fundamental constructs. Within this principle, space-time can be seen as a byproduct of deep information processes, which changes our understanding of reality itself. It is forcing scientists to rethink the building blocks of the universe, indicating that at a deep level, the fabric of reality may be more like a vast cosmic database. The study of the holographic principle is stimulating ongoing research in theoretical physics and cosmology, pushing the boundaries of our knowledge of the dynamics of the universe. Such groundbreaking theories raise questions about the very essence of existence, changing our understanding of the interactions of matter, energy, and the structure of space-time itself. The fate of the universe depends on the subtle interplay of various factors, most notably its rate of expansion and the total amount of matter and energy it contains. Observations show that the universe has been expanding since the Big Bang, and recent research has shown that this expansion is accelerated by a mysterious force known as dark energy. This phenomenon raises the possibility that the universe may continue to expand indefinitely. If the current trend of accelerating expansion continues, the universe could enter an epoch known as the Big Freeze. In this scenario, galaxies would grow increasingly distant from each other, stars would burn out, and eventually the universe would become dark, cold, and devoid of significant activity. Such a long-term outcome would mean the end of any semblance of structured cosmic phenomena, resulting in a vast silent space where only the isolated remnants of stars can exist. Conversely, a scenario known as the Big Bang is possible. This would happen if the gravitational pull of all the matter in the universe is strong enough to overcome the force of dark energy, eventually stopping the expansion and reversing it. In this case, everything could fall into a singularity reminiscent of the state of the universe before the Big Bang. However, new observations show that dark energy is the dominant force in the universe, making the Big Bang less likely. The ongoing debate about the end of the universe concerns not only physics, but also philosophy. As scientists continue to look for dark energy phenomena and other aspects of the universe, our understanding of the end of the universe is growing. The question of whether the world will continue to expand or undergo a violent revolution is one of the most interesting questions in the world. Looking into the very long-term future of the universe, extending trillions of years into the future, we are faced with some profound and intriguing scenarios arising from our current understanding of cosmic dynamics. Assuming that the prevailing trend of accelerated expansion caused by dark energy continues, the universe is likely to enter a state often referred to as the Big Freeze. In such a future, galaxies will be infinitely distant from each other, resulting in a cosmos characterized by vast emptiness and isolation. In this distant reality, the life cycles of stars will unfold in dramatic ways. Most stars will eventually exhaust their nuclear fuel and gradually fade away, leaving behind remnants such as white dwarfs, neutron stars, or black holes. Over time, these remnants will cool and darken, which would result in a dark universe with no active star formation. Galaxies become rare, and the structures of the universe become almost invisible against the vast backdrop of a dark sky. In addition to the fate of stars, black holes make up most of the Earth. Mysterious regions of space-time, with a strong gravitational pull that emit no light. But black holes don't last forever. It's expected to disappear after many millions of years by a process known as Hawking radiation. A burst of radiation means that supermassive black holes simply disappear, helping to cool the universe's environment. When time reaches uncharted territory, the world may perish in a state known as heat stroke. This situation takes place in a world where all energy is distributed, resulting in some form of thermal equilibrium. There are no major changes or major events in this world, so it remains a quiet place. This is causing people to question the nature of existence and the long-term significance of global evolution in a seemingly fixed and unchanging world. The potential ends of the universe, characterized as the Big Bang and heat death, are two contrasting scenarios shaped by the fundamental forces and energy dynamics at work in our cosmos. Each scenario offers a different picture of what might happen over time, determined primarily by the mysterious nature of dark energy, which is currently driving the accelerated expansion of the universe. The Big Gap. This is a fascinating theory that envisions a future where the expansion of the universe continues to accelerate uncontrollably. In this scenario, the force of dark energy becomes so dominant that it begins to override all other interactions, from the gravitational pull that holds galaxies together to the forces that bind atoms together. As the rate of expansion increases, structures of all scales, from galaxy clusters to individual stars, and even atoms themselves, will eventually be torn apart. This dramatic finale will unfold over a timeline that could span billions of years, culminating in a universe where everything is torn apart in a cataclysmic finale. On the other hand, the heat death scenario is based on the concept of thermodynamic equilibrium. Over an incredibly long time, as stars die and galaxies disperse, the universe will reach a state where all energy is evenly distributed. In this cold, dark future, activity would be minimal. Stars would not shine, life forms would not thrive, and interactions to create dynamic events would not exist. Such a universe would be stable, but completely devoid of structure and change, resembling an unlit theater after the final curtain falls. When speculating about which scenario is more plausible, current observations show that dark energy does indeed accelerate the expansion of the universe. However, the nature of dark energy remains one of the most significant mysteries of cosmology. Depending on how dark energy evolves over time, it could lead us to either a large rift or a gradual heat death. As research continues, the questions surrounding these ultimate fates underscore the profound complexity of our universe and the forces that govern its destiny. The question of whether the universe is finite or infinite in extent presents a major challenge to cosmologists and researchers. Both possibilities offer intriguing implications that shape our understanding of the cosmos. Modern observations show that the universe is vast and may even appear flat, judging from measurements of the cosmic microwave background radiation, but the question of whether it is extending infinitely or collapsing in on itself remains an active area of research. If the universe is finite, this implies that there is a finite volume of space with a finite amount of matter, energy, and structures that we observe. A finite universe could potentially take the form of a higher dimensional sphere or similar geometric construct, allowing for a scenario in which traveling in one direction could eventually lead one back to one's starting point. Such a finite universe raises questions about its boundaries, if any, and what lies beyond. The possibility challenges our intuition, forcing us to consider the nature of existence and whether there is anything beyond our universe. In contrast, an infinite universe implies that space is infinitely expanding in all directions, filled with an infinite distribution of galaxies, stars, and interstellar matter. The point of infinity represents the ultimate view of reality. Of course, no matter how far one travels, one has to discover new areas of the cosmos that may have many different aspects of life. This concept expresses the idea of infinity of ways, that any set of matter can exist anywhere in the common realms. The concepts of an infinite universe and an infinite universe go beyond simple measurement and geography. It addresses philosophical questions about the nature of the world and our place in the world. An infinite universe can point to either a beginning or an end point, and an infinite universe challenges notions of individuality and a limited form of reality. Scientists are exploring this profound question, trying to understand the relationship between perception, theory, and the basic nature of space and time. Many end-of-the-world scenarios are emerging based on new knowledge and worldviews. These phenomena depend on the relationship between the expansion of the universe, dark energy, and the density of matter and energy. One of the leading possibilities is the Big Freeze, which predicts that the universe will continue to expand at an accelerating rate. In this scenario, the main driving force is dark energy, creating a future in which galaxies grow farther apart, stars burn out, and matter becomes increasingly rarefied. Eventually, the universe will move into a state of thermodynamic equilibrium characterized by gradual cooling over trillions of years. In this case, cosmic activity would decline, leading to a dark and empty universe with only remnants of stellar processes scattered throughout the void. In contrast, the Big Rip presents a more dramatic scenario.
According to this hypothesis, if dark energy continues to grow and is ignored, it could eventually overwhelm all other forces in the universe. This causes the rate of expansion to increase, tearing galaxies, stars, planets, and even atoms apart. The end of the world will be the final catastrophe that will eventually destroy all structures. While this fate may seem ominous, it is a misconception based on our understanding of dark energy. Another phenomenon is the Big Squeeze. This outcome could happen if the density of matter in the universe is dense enough to stop its expansion, causing gravitational forces to eventually pull everything together. In such a state, the universe will contract, culminating in a singularity similar to the initial state from which it originated. Although current observations lean toward the expansion continuing, the dynamics of dark energy can change over time, making the Big Bang a possibility for some models of the universe. Each of these scenarios reflects the intricacies of cosmic evolution and the mysterious nature of dark energy. As researchers continue to gather data and refine their theories, understanding the ultimate fate of the universe promises to reveal deeper truths about the cosmos and our place in it.